In our previous session, we had learned about how to use Bootstrap in context to regression. Today, we would be seeing one more application of regression of Bootstrap in context to regression, but this time not on linear regression, but on something called the resistance regression. So, this resistant regression is a method which can accommodate a lot of outliers. So, we would be using a particular form of this method called the least trimmed square, and we would be using Bootstrap to find out what are the estimates or standard error of the regression coefficients. Now, it is well known that ordinary least square estimates of a regression model are very sensitive to even a small amount of contamination of the data. So, in such situations, a popular method that can be used is the least trimmed squares. Here, one minimizes summation I runs from 1 to q epsilon I square, where I within parenthesis indicates sorting, and this sum is up to q, where q is some number less than n. This method has a very high breakdown point because it can tolerate a large number of outliers depending on how q is chosen. This method or the LTS is an example of resistant regression method, and resistant regressions are good for dealing with data where we expect there to be a certain number of observations where we want to have no weight in the analysis. So, we have certain number of outliers in the data, and we do not want to have any weightage on those outliers. So, in such situation a resistant method comes good. Now, let us to apply the resistant method, we would be using a data set called Gala. This data set is in the library Faraway. So, the first thing that we do is we load the library Faraway, and once we load the library Faraway, we would be using the data Gala. So, question mark Gala would give us the description, and as per the description, the data contains 7 variables of 30 Galapagos islands, and the relationship, the variables are the number of plant species and several geographic variables. So, the variables that it has is species, which is the number of plant species found in the island, endemics, the number of endemic species, area, the area of the island in square kilometers, elevation, the highest elevation of the island, nearest, the distance from the nearest island, S cruise, the distance from Santa Cruz Island, and adjacent, the area of the adjacent island in square kilometers. Now, this data is in the package Faraway. Now, first we fit a simple linear model using the LM command. So, once we fit the LM command, so LM species explained by area plus elevation plus nearest plus S cruise plus adjacent, data equal to Gala, and store it in an object called G underscore LM. Then we can run summary G underscore LM to get the summary of the fit, and we see that the number of species, in explaining the number of species, it is only elevation and adjacent, these two variables are coming out to be significant, the remaining is not. So, once we fit the linear model, we can plot that object. So, plot G underscore LM, and if we see the Cook's distance plot, the Cook's distance for the least square fit shows that the island of Isabella is very influential. So, if we fit the same model, but this time removing the island Isabella. So, basically the same fit, but this time with the extra argument which is the subset command, and says that Isabella should not be there in the row names, and then run and store it in another object called G underscore LM1, and then summary G underscore LM1, and we see that now the variable area has become significant along with elevation and adjacent. Now, we do the same thing, but this time using the least stream square regression. Now, that can be implemented in the library robust base. So, the robust base library has a function called LTS reg, which implements the resistant regression. So, we use library robust base to load the library and then fit the LTS regression using the command LTS reg, and if we see summary G, we see that already area comes out to be significant and nearest screws and adjacent are all significant, but elevation is not. So, this is in contrast to our finding from the linear model. Now, let us see how we can use Bootstrap in context to this LTS regression model. So, the idea is to do the bootstrap of the residuals, and then we can add that residuals to the fitted values of the LTS regression and once again perform the LTS regression, extract the coefficients and store the coefficients. Now, to do that in R, we define a matrix called Bquef, and if you see here there are 6 coefficients. So, we take all those. So, the matrix is having 6 columns, each column stands for 1 coefficient, and the rows we take 1000 rows. So, that means we would be doing 1000 iterations, or we would be taking 1000 bootstrap samples, and we initialize all the values in the matrix in each cell of the matrix to be 0. So, we say Bquef is a matrix with 0, 1000, 6, and then we use the for loop saying that for I in 1 to 1000 we need to perform a certain set of things. What? First, we need to generate the new y's or the y star. So, that is new y is fitted G plus residual G, and on the residual G we take a sample of size 30 replacement with replacement and create the new y vector. So, once this new y vector is created, we create a data frame called new data inside the loop. That means, we would be creating 1000 such data frames, and each data frame has all the 6 explanatory variables of the Gala data, and this time the species variable is being replaced by the new y variable, and for each of these 1000 data sets we would be running the least LTS regression. Once we run the LTS regression, we would be extracting the coefficient and storing it in the ith row of Bquef. So, once we run this command, and I have used set.seed123 for reproducibility. Now, Bquef is the matrix which holds 1000 bootstrap estimates of the 6 coefficients. So, if we just use apply Bquef comma apply Bquef comma 2 comma mean, we get the mean estimates. Now, note that the bootstrap estimates are a bit different from the least square estimates. So, to see whether we can also use the Bquef to find the quantiles of each of the regression coefficient. So, if we use bquef quantile of the second column is the area variable and C 0.025, 0.975, then we get the 95% bootstrap confidence interval, percentile based confidence interval, and that comes out to be 1.4713 and 1.597, which does not include 0. So, that means area is a significant explanatory variable. So, we can plot the density to see what is the distribution, and if we plot the density, we get the value of the coefficient of area, and the graph shows the total coverage of the coefficient of area. So, we can have the quantiles drawn also on it, and we can draw what is the mean bootstrap estimate by using abline V equal to mean bquef comma 2, that is the second column of bquef. Color is equal to red, and now we see that here this red line, the coefficient the confidence interval does not contain 0, meaning that area has an effect on species. In today's session, we have seen how we can use bootstrap along with the resistant regression to deal with outliers present in the regression model or in the regression data. Now, while doing so, we have written scripts in R, and those scripts we are repeatedly running for b number of samples or n number of samples. There is a package in R called boot which performs the bootstrap. The boot package is a particularly flexible package where we are just to provide the function that we need to run, the data set on which it needs to run, and the number of samples it needs to run. And then the boot function calculates all the necessary statistics associated with bootstrap. We have previously used the boot function, but have not seen the entire utility of the package. So, in the next session, we would be dealing with the boot package in R.